Hello everyone, today we will be doing a speed of sound lab using a resonance tube. So let's take a look at what equipment we will have and then we'll start listing some givens. So as you can see here, I have a large graduated cylinder filled with water, and then that white tube there, the smaller tube, is called the resonance tube. We also have a meter stick, of course, and a tuning fork. And you can see there that the frequency is 329.6 hertz. I will be smacking that on my boot in order to get the noise. And then we'll be moving that above the tube to hear it resonate. Okay, so let's talk about what our goal is and how we're going to get there. Our goal is to figure out the speed of sound in the classroom using resonance. So we have that tuning fork. It has a frequency, like I said, of 329.6 hertz. And what you'll see me do in a minute is I hit the tuning fork on my boot in order to get the sound. And then I hold the tuning fork over the resonance tube, which is that smaller white tube, and I adjust the height of that resonance tube. And what I'm listening for is the spots where the sound resonates, where I can hear it resonating inside of that white tube. It's bouncing off of the water that's at the bottom of the tube. So that distance, that height from the top of the water to the top of that white tube should be equal to a quarter of a wavelength. And once I can figure out what the full wavelength is and I know frequency, I can calculate the speed of sound in the classroom using the wave equation. Now, the reason we need the diameter of our resonance tube is because we technically do have to account for that small column of air that's between the top of the white tube and the tuning fork. I'm not holding the tuning fork right up against the resonance tube because then the sound would be muffled. So we are using that diameter, multiplying it by 0.4, and then adding that to our length of the tube that we measure. So that will help us actually be more accurate in saying that this length is equal to a quarter of a wavelength. So you can hear in the video, I know it's kind of hard, but I move the tube up and down, and there's a spot where the sound sounds different. You can hear it moving through that tube, and then I measure that length. I listened for that spot of resonance. Hopefully you could hear that in the video. And then I measured the length of the resonance tube. So I was measuring from the surface of the water to the top of that white tube, and I got 24.5 centimeters. So using that in conjunction with the diameter of the resonance tube, I should be able to figure out what a quarter of a wavelength is. Therefore, I know what a full wavelength is, and I know frequency, so I can use the wave equation to figure out the speed of sound in the classroom. Now, the speed of sound at 0 degrees Celsius is 332 meters per second. And for every degree Celsius you go above 0, the speed of sound increases 0.6 meters per second. The temperature of the classroom was 20.5 degrees Celsius. So see if you can figure out, according to that information, what the actual value of the speed of sound should have been in the classroom, and calculate the percent error between our experimental data and this actual value.